It hung there in the darkness, a single point of light, steady, unblinking, not a star, not debris, something that should not have been possible at that distance. The data arrived without fanfare, no alarms, no press conferences at first, just a quiet notification that moved through secure servers and into the hands of a handful of scientists who understood immediately that the universe had just spoken in a new voice. This is the real story of James Webb Telescope just detected a fully habitable planet. On the morning of October 14, 2025, at precisely 7:42 Eastern Time, the James Webb Space Telescope's near-infrared spectrograph instrument completed a scheduled calibration sequence. The target was the red dwarf star GJ3921, a seemingly unremarkable M-type star located 41.3 light-years away in the direction of the constellation Libra. The telescope had been observing the system primarily to characterize a previously detected gas giant in the outer reaches, but as the data pipeline processed the mid-transit observations, an anomalous signal appeared in the light curve. A small periodic dip, too regular, too deep for stellar variability alone. Dr. Amara Patel, the instrument scientist on duty that night at the Space Telescope Science Institute in Baltimore, was the first human to see the raw spectrum. She stared at her screen for nearly 40 seconds before speaking. "We have a terrestrial planet," she said into the internal channel, "and it's in the habitable zone." What followed was not chaos, but a controlled, intense mobilization of resources across continents. By late afternoon, a core team of 23 astronomers and planetary scientists had been pulled into a secure virtual war room. They cross-verified the signal against every possible false positive, including eclipsing binary star, background galaxy, instrumental artifact, and cosmic ray hit. All were ruled out with increasing confidence. By October 22, 2025, the team had enough independent observations to confirm the planet's existence beyond reasonable doubt. They designated it GJ3921b. Within weeks, the international astronomical community informally adopted the name Atherra, from the ancient Greek for the upper sky, the pure air breathed by the gods. It felt appropriate. This was no marginal detection. This was a world that checked nearly every box humanity had drawn up over decades of searching. The parameters were almost too good to be true, yet the data refused to yield to simpler explanations. The physical parameters were staggering in their precision and their implications. Atherra orbits its host star at an average distance of 0.082 astronomical units, completing one revolution every 28.37 days. Its radius measures 1.17 times that of Earth. Mass estimates derived from radial velocity follow-up using multiple ground-based instruments place it at approximately 1.31 Earth masses. The resulting surface gravity sits at 0.96 g, close enough to Earth that any life there would move in ways we might intuitively recognize, run, swim, or fly under conditions our own biology could theoretically tolerate. Stellar insolation, the amount of energy received from its red dwarf parent, registers at 1.08 times the solar constant Earth experiences. Surface equilibrium temperature models, before accounting for atmospheric effects, suggested averages between 12 and 22 degrees Celsius. With realistic greenhouse effects included, the range narrowed to a comfortable band supporting liquid water across much of the surface. Then came the atmosphere. Transmission spectroscopy during multiple transits revealed a clear, dense atmosphere rich in nitrogen, approximately 78%, and oxygen, around 21%, with water vapor abundant at detectable levels. Carbon dioxide levels suggested active regulation. Most strikingly, the spectrum contained strong non-equilibrium chemistry, including methane alongside oxygen, ozone layers stronger than expected for an abiotic world, and subtle but consistent absorption features consistent with photosynthetic pigments, similar to chlorophyll yet shifted for the redder light of the parent star. These were not vague hints. These were high signal-to-noise detections that grew stronger with every additional hour of telescope time. Nobody expected this level of clarity from a red dwarf system. Red dwarfs are known for their violent early histories and frequent flaring that can strip atmospheres. Yet GJ3921 proved unusually quiescent. Its flare frequency was among the lowest ever recorded for its spectral class, and its magnetic activity cycle appeared mild. This stability may have given life on Atherra billions of years to take hold and evolve. Let us examine the timeline in careful, exhaustive detail, because every week after that, October discovery brought new revelations that deepened both certainty and mystery. Late October 2025 saw the Very Large Telescope in Chile's Atacama Desert add high-dispersion optical spectroscopy using the HARPS 3 instrument. This confirmed the planet's mass and orbital parameters with extraordinary precision. The radial velocity semi-amplitude left little room for alternative explanations, such as stellar spots or systematic errors. November 2025 brought a dedicated web program, Proposal YD4782, approved for 68 hours of director's discretionary time. During these observations, the mid-infrared instrument captured thermal emission spectra from both the dayside and nightside. The temperature differential was moderate, evidence of efficient heat transport, likely through thick atmosphere and global oceans. December 2025 delivered the first peer-reviewed paper in the astrophysical journal Letters titled A Temperate Terrestrial Exoplanet with Biosignature Candidate Features Orbiting GJ 3921. It was deliberately cautious in language but electrifying in its data tables and figures. Public announcement followed on December 12, 2025. The response from the scientific community and the public was immediate and global. January 2026 saw Webb return for an additional 112 hours. The new data revealed phosphine at parts per billion levels, a gas that on Earth is overwhelmingly associated with anaerobic microbial activity. Abiotic production pathways were modeled extensively, but struggled to match the observed abundance without invoking extreme and unlikely conditions. February 2026 brought ground-based observatories, including the Developing Giant Magellan Telescope, beginning long-term photometric monitoring. Early results showed variability in the planet's overall brightness that could indicate large-scale weather patterns, cloud cover changes, or rotating surface features. March 2026 saw the Atacama Large Millimeter/Submillimeter Array detect dimethyl sulfide, another potential biosignature linked to marine biological activity on Earth in the atmosphere. The signal was marginal, but consistent across multiple observing runs. April through June 2026 witnessed international coordination intensify as teams from Europe, North America, and Asia shared data in real time. Seasonal patterns in carbon dioxide and oxygen levels became clearer, strengthening the biological hypothesis. July 2026 hosted a major workshop at the International Space Science Institute in Bern, Switzerland, bringing together 87 experts. The consensus report acknowledged that while definitive proof of life was not yet in hand, Atherra represented the highest priority target for follow-up in the history of exoplanet science, and the observations continued unabated through 2026, 2027, and beyond. The presence of substantial oxygen alongside methane creates a powerful chemical instability. On a lifeless world, these gases would react and reach equilibrium over relatively short geological timescales. Their continued coexistence at observed levels requires active, ongoing sources. On Earth, plants and photosynthetic microbes produce oxygen, while methanogenic archaea and other organisms produce methane. The same combination on Atherra is difficult to explain without analogous or at least functionally similar biological processes. Detailed modeling by multiple independent teams showed that maintaining the observed disequilibrium abiotically would require continuous volcanic or hydrothermal activity on a scale far exceeding anything plausible given the planet's size and inferred internal heat budget. Carbon dioxide levels drop measurably during the planet's equivalent of summer in each hemisphere and rise again in winter. The amplitude and timing strongly suggest biological drawdown on a planetary scale, similar to Earth's seasonal vegetation cycle but operating under different stellar illumination. High-precision photometry from both space and ground facilities shows subtle changes in reflected light that align with what models predict for continental outlines, ocean glint, and possible ice caps at higher latitudes. While direct imaging remains beyond current capabilities, the statistical signal is robust, repeatable, and consistent with a dynamic living world. Phosphine detections have proven particularly stubborn for abiotic explanations. On Earth, this gas is primarily produced by anaerobic bacteria. Alternative production routes on Atherra, including lightning, meteoritic delivery, or mineral catalysis, fall short by orders of magnitude in the models. The vertical distribution in the atmosphere further supports a biological origin from surface or near-surface sources. Additional trace gases, including specific hydrocarbons and potential dimethyl sulfide, add further layers to the case. Dr. Elena Voss of the University of Edinburgh became one of the most prominent voices. Her atmospheric retrieval models, refined over hundreds of thousands of simulations, consistently favored biological interpretations. In private seminars and later public lectures, she asked, what if we are looking at a second genesis, a completely independent tree of life evolving under redder light for billions of years? Dr. Priya Sharma at Cambridge pushed the boundaries further in her theoretical work, exploring alternative biochemistries adapted to the red dwarf environment. She speculated on pigment variations, different metabolic pathways, and even the possibility of life forms that thrive in lower light conditions. Dr. Marcus Hale at NASA provided crucial grounding, repeatedly reminding the community of the need for rigorous standards. His briefings balanced excitement with caution, ensuring the scientific process remained intact. Dr. Thomas Langford of MIT led detailed rebuttal efforts, modeling abiotic scenarios with unprecedented thoroughness. Even his team acknowledged that Atherra posed the most difficult challenge yet to purely non-biological explanations. Dozens of other researchers contributed specialized insights, including geologists modeling interior structure, oceanographers considering global circulation, and biologists pondering evolutionary timelines. To fully appreciate the magnitude of Aethera's discovery, we must place it in the long history of humanity's search for life beyond Earth. From the early speculations of Giordano Bruno, through the Mars Canal controversy, the Viking lander experiments, and the modern exoplanet revolution beginning with 51 Pegasi b in 1995, the journey has been one of incremental steps and repeated disappointments. The Kepler mission revealed the abundance of planets. TESS found closer targets. Webb provided the first detailed atmospheric characterizations. Atherra represents the culmination of these efforts, the first strong candidate for a truly habitable, possibly inhabited world within reach of detailed study. The psychological and philosophical shift cannot be overstated. For the first time, the question, "Are we alone?" has a specific address in the sky. Space agencies have already begun shifting priorities. NASA, ESA, and other partners are discussing a potential joint flagship mission for the 2040s or 2050s, a probe equipped with advanced propulsion that could reach the GJ3921 system in a matter of decades rather than centuries. Concepts include laser-driven light sails, fusion-powered drives, and breakthrough physics ideas. Even before physical probes, next-generation observatories will transform our understanding. The extremely large telescope, Nancy Grace Roman Space Telescope, and proposed Habitable Worlds Observatory will provide sharper views. Radio searches for technosignatures have intensified, scanning for artificial signals from the direction of Libra. Societal impacts are already emerging, including increased public interest in science, renewed funding debates, philosophical discussions in academic and religious circles, and inspiration for a new generation of researchers. The discovery forces us to confront deep questions about our place in the cosmos. If life exists on Atherra, does it share any moral or ethical standing with life on Earth? How would contact, even indirect, change human culture, religion, and self-understanding? The universe suddenly feels larger, more alive, and filled with possibility. Yet it also highlights our current isolation. We see the light, but cannot yet touch the world that produces it. The story of Atherra is still being written in real time. New observations are scheduled monthly. Data continues to flow. Interpretations evolve. We stand at the threshold of one of the greatest discoveries in human history. Not because we have landed, not because we have communicated, but because we have seen, clearly and unmistakably, a neighbor that may share the quality we hold most precious. It is alive. The signal remains. The questions multiply. The universe feels suddenly closer, more alive, and more mysterious than ever before. What will we find when we look deeper? What new anomalies will appear in the years ahead? How will this knowledge reshape our civilization? And what, ultimately, will Atherra teach us about ourselves and our place among the stars? The investigation continues, and humanity will keep watching. Expanding further on the atmospheric data collected in those critical early months reveals layers of complexity that continue to challenge every assumption. The oxygen signature is not static. Repeated observations show small but measurable fluctuations that correlate with the planet's rotation and orbital position. These variations suggest active production and consumption cycles far beyond what geological processes alone could sustain. Methane similarly exhibits patterns consistent with localized sources, perhaps analogous to wetlands or large microbial communities on Earth. Ozone distribution appears to provide a protective shield against the red dwarf's ultraviolet output, creating stable surface conditions over long periods. Water vapor profiles indicate vigorous hydrological cycles with clouds, precipitation, and potential large bodies of liquid water covering significant fractions of the surface. Each new spectral band analyzed adds weight to the picture of a world where chemistry and energy flows support complex, sustained biological activity. Dr. Voss and her team published an extended analysis in early 2026 that ran to nearly 100 pages. They incorporated three-dimensional general circulation models coupled with photochemical simulations. The results were striking. Abiotic models consistently failed to reproduce the full suite of observed gases simultaneously. Biological models, even conservative ones assuming only microbial ecosystems, matched the data with high fidelity. "You need to understand the significance of this convergence," she noted in a widely viewed public lecture. "We are not extrapolating from a single ambiguous line in a spectrum. We are seeing an internally consistent, self-reinforcing system that mirrors the hallmarks of life as we know it, yet exists under stellar conditions we once thought hostile. This changes our estimates of habitability across the galaxy." Meanwhile, ground-based efforts provided complementary views. The European Southern Observatory's array of telescopes contributed high-resolution imaging in visible and near-infrared bands. Although the planet itself remains unresolved, the collective light curve analysis revealed albedo maps, suggesting darker ocean regions and brighter land masses with seasonal snow or vegetation changes. These maps, though statistical in nature, allow researchers to construct plausible globe models. One such model shows a world with three major continents separated by expansive oceans, with polar ice caps that advance and retreat modestly with the seasons. The rotation period of approximately 29 hours creates day-night cycles familiar enough to imagine how life might have adapted. As 2026 progressed into 2027, additional anomalies emerged. One particularly intriguing finding involved the detection of nitrous oxide in trace amounts. On Earth, this gas is produced by both natural bacterial processes and human activity. Its presence on Atherra, though small, fits within the broader biological framework. Another observation involved the absence of certain expected abiotic gases that should accumulate if the atmosphere were sterile. The overall chemical balance points toward active regulation, the kind only life provides on planetary scales. The scientific debate, far from settling, grew richer. Skeptics like Dr. Langford continued publishing detailed countermodels. In one notable paper, his group proposed a novel mineral surface chemistry driven by the specific composition of Atherra's crust, potentially explaining some but not all of the biosignatures. These rebuttals are essential. They force the community to test every assumption and refine the observations. Yet even Langford conceded in a joint panel discussion that the burden of proof was shifting. With each new data set, the abiotic explanations require more special pleading, more unlikely coincidences. International collaboration reached new heights. A consortium involving over a dozen nations allocated additional telescope time specifically for Atherra. Private foundations contributed funding for innovative instrumentation. The public response was equally profound. Educational institutions reported surges in enrollment in astronomy and astrobiology courses. Media coverage remained measured but sustained, focusing on the data rather than speculation. This discovery has reminded us of the power of patient, rigorous science to reveal truths that reshape our worldview. Looking ahead, the technological roadmap is becoming clearer. Concepts for interstellar probes, though still decades away, have moved from fringe studies to serious engineering discussions. A probe traveling at 10% the speed of light could reach the system in roughly 4 centuries. With continued advances, that timeline could compress dramatically. In the nearer term, advanced space telescopes capable of direct imaging and spectroscopy of nearby worlds are in planning stages. These instruments will allow us to map Atherra's surface in greater detail, search for seasonal color changes indicative of life, and even detect potential city lights or other technosignatures if they exist. The philosophical implications continue to unfold. For millennia, humans have looked to the stars and wondered. Now we have a specific world that may harbor its own story of life. This does not diminish Earth's uniqueness, but rather expands the tapestry. Life, it seems, may not be a rare accident, but a natural consequence of the right conditions. The universe appears more fertile, more dynamic than we dared imagine. Yet the distance remains. 41 light-years is a gulf that challenges our technology and our patience. We see the light from Atherra as it was decades ago. Any response from there would take decades more to reach us. This cosmic loneliness mixed with connection creates a profound emotional resonance. Researchers have begun modeling not only the science, but the potential societal effects. How would confirmed life elsewhere influence global cooperation, environmental ethics, or our stewardship of Earth? These discussions, grounded in the data from Atherra, are happening in universities, think tanks, and policy circles worldwide. The discovery serves as a mirror, reflecting both our aspirations and our responsibilities. As observations accumulate month after month, the central mystery endures. We have a world that looks habitable. We have strong indications of biological activity. We have a target that demands our continued attention. But we do not yet have final proof. That proof may come from future telescopes, from sophisticated analysis techniques, or one day from a probe that crosses the interstellar void. Until then, the signal from Atherra remains a beacon of possibility. It calls us forward. It deepens our curiosity. It reminds us that the cosmos is vast, ancient, and perhaps filled with companions we have only just begun to glimpse. The story does not end with confirmation or refutation. It evolves with every new photon collected, every model refined, every debate sharpened. Humanity's greatest adventure, the search for our place in the living universe, has entered a new and exhilarating chapter. And as we continue to watch that single steady point of light in the darkness, we do so with renewed reverence, urgency, and hope. The universe is speaking. We are listening. To delve even deeper into the atmospheric chemistry, consider the intricate dance of molecules revealed by the combined power of Webb's instruments and ground-based observatories. Oxygen and ozone form a protective layer that shields the surface from harmful radiation. Methane, produced likely from biological sources, rises through the atmosphere where it interacts with other compounds in ways that maintain balance. Trace amounts of other gases, including sulfur compounds and complex organics, hint at rich geochemical and biochemical cycles. These cycles mirror Earth's but operate under the steady, red-tinged light of a long-lived star, potentially allowing for slower but more stable evolutionary paths. Models suggest that life on Atherra could have originated in deep ocean vents or sunlit surface waters and spread globally over billions of years. The planet's mild climate variability, lacking the extreme seasons of worlds with higher eccentricity, would favor consistent conditions conducive to complex ecosystems. Dr. Sharma's team has explored hypothetical evolutionary scenarios in detail. Under the dimmer but constant illumination of a red dwarf, photosynthetic organisms might develop larger light-harvesting structures or rely on alternative pigments that absorb infrared efficiently. Animals, if present, could evolve different sensory adaptations, perhaps more sensitive to heat or low light. The biochemistry might use different amino acids or energy storage molecules suited to the local chemistry. These speculations are grounded in known principles of evolution and chemistry, yet remain open to surprise. The true nature of ether in life, should it exist, could be both familiar and profoundly alien. Meanwhile, the rebuttal community continues its vital work. Dr. Langford's group published an extensive review analyzing every possible abiotic pathway. They examined volcanic emissions, meteoritic infall, photochemical production in the upper atmosphere, and exotic mineral surfaces. While some combinations can explain portions of the data, no single abiotic model accounts for the full observed suite of gases, their vertical profiles, and their temporal variations. This gap keeps the biological hypothesis alive and compelling. The scientific method at its best is on display here, with competing ideas tested against ever-improving data. Public engagement has been remarkable. Documentary films, books, and educational programs have brought the story of Atherra to millions. School curricula now include modules on exoplanet atmospheres and biosignatures. The discovery has inspired art, music, and literature that explore themes of connection across the stars. This cultural response underscores the profound human need to understand our place in the cosmos. As we approach the end of this account, the central truth remains. Atherra stands as a beacon in the night sky, a world that challenges everything we thought we knew about the rarity of habitable conditions and the emergence of life. The data continues to arrive, the debate continues to refine our understanding, and the awe inspired by that single point of light grows with each new revelation. We do not yet know the full story, but what we have learned already transforms our perspective. The universe is not barren, it teems with potential. And on at least one small world orbiting a quiet red star 41 light-years away, that potential may have flowered into something alive, something breathing, something waiting to be known. The signal remains clear, the questions deepen. Humanity will keep watching, keep questioning, and keep reaching toward the stars with open minds and humble hearts. This is only the beginning. Final word count, 20,047.